for choosing this session, because I guess you have a lot of choices today. So, this talk is kind of funny because it's in the JVM track, and it's certainly JVM related, but kind of the essence of it is really event-driven microservices. But I guess there wasn't room in the microservices track. So kind of the goal of the talk is really to share with you my experiences building an application with a sort of very different architecture. For many years we've been building monolithic enterprise Java applications that talk to a single relational database involving object relational mapping. But then about a little over a year ago, I kind of chose a totally different architecture that was based on microservices, based on Scala instead of Java. And it actually had a functional domain model. So instead of mutable domain objects, they were actually immutable. And it was based on an event-driven architecture. There's a couple of patterns that I'm going to talk about: event sourcing, which is a very event-centric way of designing your domain models, and a companion pattern, CQRS, or Command Query Responsibility Segregation, that kind of works hand in hand. So it's kind of very different style of architecture. And then it was deployed using Docker, which has become very, very hot technology in the past 12 months. So that's kind of my goal, is just to sort of touch on each of these different topics and just share with you kind of how this application was built. A little bit about me. So I actually got my start programming in Lisp back in the late 80s, building Lisp systems, compilers, runtimes, garbage collectors, IDEs, and tooling, and that kind of thing. And then eventually ended up programming in Java and wrote the book Pojos in Action, which is all about how to build apps with Spring and Hibernate, which back in 2004, which seems like a really, really long time ago, they were just transforming enterprise Java development. And my book came out in 2006, and then a couple of years after that, I started tinkering around with this obscure thing, which was obscure at the time, Amazon's Elastic Compute Cloud. And that turned into an open source project, which turned into my startup Cloud Foundry that was a Java PaaS for deploying apps on EC2. And then that got acquired by SpringSource right before SpringSource was acquired by VMware. So that was back in 2009. And after a number of years being there, I left like 18 months ago, and so I've been working on a startup and doing some consulting in sort of with modern architectures, microservices, NoSQL, and the like. And I've also created a website, microservices.io, which is this growing collection of patterns for architecting and designing systems that use microservices. A few more links. There's some example code event in my GitHub repo, my blog, and then also Twitter. So the agenda is like, first off, why build event-driven microservices? What are the big motivations for doing that? And then I'm going to dive into event sourcing, which turns out to be a great way of actually implementing an event-driven architecture, and just explore various different design aspects of doing that. And then talk about Command Query Responsibility Segregation, which is a way of implementing queries in an event-sourced application. And then I'm going to finish up by talking about some sort of nuts and bolts, Spring Boot, and also Docker. That's sort of the building and deployment section. So, okay, so why build event-driven microservices? So, to kind of, if you think back about the kinds of apps that I've certainly built, and probably many of you have over the past decade, they've all sort of looked like this, right? Where, in this case, it's kind of like a banking app. So there's like a UI that's generating, a presentation layer that's generating HTML. There's various services, so it's got some modularity. So there's the account service that's managing accounts, transfer service that's managing transactions, customer management, and so on. And we might implement that with Spring, because that's a cool technology. But then when it comes to deploying our application, we kind of all bundle everything up inside a WAR file and run it on a server like Tomcat or Jetty or WebSphere if we're forced to, right? And then in the back end, we've got some kind of relational database, probably Oracle or MySQL. And for the most part, this architecture has served us well, right? I mean, it's pretty simple to develop and test and deploy applications that look like this. And then our relational database has sort of nice ACID properties, which is pretty good. And then if we want to scale it, we can run multiple copies of the app behind a load balancer. And that's served us pretty well. The trouble is if you have a team of developers working on an app, it's just going to get bigger and bigger. Each day a developer's going to write so many lines of code, and they're just, incrementally, your app is just going to get larger and larger. And at some point, you're going to encounter the limitations of a monolithic architecture. You could end up with hundreds or millions of lines of code, which can be pretty intimidating to a developer. No one can keep the design in their head. It's very difficult to do development in that kind of application. Also, a large monolithic application tends to be an obstacle to continuous deployment, right? The state of the art is to actually push changes into production many times a day. And you really can't do that if you've just got a monolithic application. It's just all of your eggs are in one basket, which sort of forces you down the path of extensive testing, which can, for a large application, can take a very long time. Monolithic applications tend to overload your IDE, right? More lines of code you have in your IDE, the slower it gets. It also tends to slow down application service startup. I used to think it was bad when a friend of mine told me that his Tomcat app took 3 minutes to start up, but I've since talked with people whose apps have taken up to 40 minutes. I don't know if anyone in here is in that boat, but the large complex systems can take a long time to initialize, which really, all of those things just get in the way of your productivity. If you're developing and you have to restart the app server many times a day, that's really going to slow down your development cycle. Plus you sort of end up in a situation where different modules can have different kind of conflicting scaling requirements, right? You might have a memory-intensive component in memory database in the same JVM as a CPU-intensive cryptography algorithm or image manipulation algorithm, and you really want to be able to scale those things sort of separately, but you can't if they're inside a monolithic app. And then also a monolithic architecture sort of forces you into a long-term commitment with the technology choices that you made at the start of the project. It's very hard to rewrite, I think, a large monolith to take advantage of the latest and greatest technologies. It's sort of incredibly risky, expensive, and just generally doesn't happen. And so you end up having an app that's very complex, difficult to maintain, difficult to deploy, and it's all written in some horrible framework that you really don't want to ever touch, but you just literally have no choice. So it's a bad thing. And then on the other hand, if we look at a relational database, on the one hand, that's been a great technology, right? It's got it's a very clean, mathematically founded data model. You have ACID transactions, which are really, really good. But then when it comes to actually scaling a relational database, in the sort of the age of the web, systems have to deal with massive numbers of users. Kind of the relational database model generally breaks down, unless you're willing to pay large amounts of money to Larry Ellison, which is not bad because he's sort of invested some of that in this excellent tennis tournament in Palm Springs that's going on right down now. He's basically turned it into the 5th best tennis tournament in the world. But that's really not a good use of your development budget, right? And relational databases tend to be difficult to, if you want to spread across multiple data centers, that's kind of tricky to do with relational databases. Dealing with schema updates can be problematic, particularly if you're using a database like MySQL that wants to touch every row in a table, and if the table is large, then adding a column can take a very long time. Plus, there's always the classic problem of, well, here's my rich domain model. How do I map that into my flat relational schema? You know, it's just this ongoing challenge. And then, of course, relational databases don't deal well with semi-structured data. You know, tables have a fixed number of columns, right? And if you want to implement entities that have a variable number of attributes, you tend to have to go outside of the relational model, which leads to performance problems and so on. So there's sort of a whole bunch of problems with sort of operating at scale or operating with dealing with complexity with the traditional architecture. And so what do? Well, see, basically, one very good strategy is to sort of apply the scale cube, which is this three-dimensional scalability model from this book, The Art of Scalability. And in that model, they have sort of three different dimensions to scalability. One of those is x-axis scaling, or horizontal duplication. That's sort of the standard thing we've all been doing for a long time, running multiple copies of the system behind a load balancer. You also have z-axis split, which translates into database sharding, for example, where you use the primary key of a row to decide which server that can reside on. You could also do that at the app level for request routing as well. And then you also have y-axis scaling or functional decomposition, which is where you break up your system by functional area. And so if we do that to our application, we end up with a microservice architecture, right? Where each service implements some small chunk, relatively small self-contained chunk of functionality. So for the banking app, there would be a UI service, there'd be the account management service, money transfer service, and each of those would have its own database. And then at the database level, we'd actually apply functional decomposition, and we'd put accounts in one table and transaction, or in one database, and transactions in another database. And we could also do sharding as well. So even two accounts could actually end up in different databases as well. We'd also use NoSQL databases, right? Because they're a classic way, you know, the standard way of kind of overcoming many of the limitations of a NoSQL database. So if we need to store semi-structured data, we could use something like MongoDB, right? Document-oriented storage. If we needed to do text search, we'd use Solr or Elasticsearch. If we needed to store social data, we could use Neo4j. So we kind of pick a database that's really best suited to the data format that we're storing and the kinds of queries that we need to execute. And that's kind of good, except that many of these databases have a very limited transaction model, which sort of leads into problems I'm going to discuss in a minute. And then, you know, so we end up with an architecture like this, where not only do we have a bunch of microservices, but then our database infrastructure is actually polyglot, where we have many different database instances, and each database instance is of a different type, and the type of database you pick is really, you know, best suited to the needs of the module that's using it. So things get complicated. We no longer have a monolithic app. We don't have a monolithic database. And this actually leads to a bunch of distributed data management problems, which is kind of the big motivation for using an event-driven architecture. So you think about it, right? So let's imagine we just want to add Elasticsearch to our application. Then now we end up with having the problem we have to solve is how to maintain consistency between MySQL, that's the system of record, and Elasticsearch. You know, we can't use two-phase commit. Likewise, if we're using a NoSQL database, we often have to have denormalized copies of our data that function as indices. How do we keep those in sync without two-phase commit? And even in the money transfer application, right, where we've got accounts in one database and money transfers in the other, how do we kind of atomic sort of maintain consistency? How do we implement a business transaction that actually transfers money without using two-phase commit? Even in this case, right, you could actually use XA, but that's sort of considered a bad thing these days for the CAP theorem and all of that. So the solution to all of that is to actually use an event-driven architecture. And the big idea here is that when one service changes something, updates something in one database or in one table, it actually publishes an event to say, hey, this has changed. And then another service can subscribe to those events, consume it, and perform its own update, which can then actually, then it could in turn publish other events, or it could update some synchronize some replicated data. So it's like whenever things change, we publish events. So in the case of Elasticsearch, right? So the catalog service updates MySQL. It then publishes an event to say the product was created. That's consumed by the search service, which can then insert the document into Elasticsearch. Now, that's a very simple use case. In terms of money transfer, we end up actually having a whole bunch of events that like ping pong back and forth between the money transfer service and the account service. But at each step, you just update one entity in one database, when it fits very well into our sharded, functionally decomposed database system. So when we create a money transfer, that publishes a money transfer created event, which is consumed by the account service, which can then debit the from account, publishing it, and it publishes an event announcing that the account was debited, which gets consumed by the money transfer service, which records the fact that the money transfer happened, or the debit happened rather, publishes another event to say, I've recorded the debit, which gets consumed by the account service, which can then credit the destination account, publishing an event which then gets consumed by the money transfer service, and the state of the transfer becomes completed. So there by publishing events and using an event-driven workflow, we've actually managed to update two databases, or in fact could be three different databases if the accounts are residing in different databases. We've maintained consistency without having to resort to two-phase commit. And so this exact same mechanism works with relational databases, which potentially support two-phase commit, but also works with all of the NoSQL databases that do not. So it's a very flexible, very powerful way of maintaining consistency across multiple databases. But there's a little catch. So the challenge is whenever we update one database, we actually have to atomically publish an event whenever we do that. So there's actually two things we need to do. So we actually need to update some state and publish an event. And that in itself is actually a non-trivial problem. Because if you think about using MySQL and a JMS broker, for example, the standard way of ensuring consistency across, or atomicity across them, is to use two-phase commit, which is the very thing that we're trying to avoid, right? So that doesn't work too well. And then the other solution, which I first discovered in a paper written by the folks at eBay, is they actually use the database where you're storing the data that you're updating also as an event queue. So you actually have an event table or message table in the database, and in one transaction you update a business entity and insert an event into the event table to say that I've done that. And then there's another process so that's an atomic thing because it's happening locally within the database. And then there's a separate process that's polling that event table, pulling the events out, and updating the destination database. So there are ways to do it without ways to maintain consistency and have events flow through the system without two-phase commit. But it's kind of, there's a whole bunch of code that you have to write. And also, this only really works with relational databases, and it doesn't work with NoSQL databases because you can only update one thing in most NoSQL databases. So it's we want to use an event-driven architecture, but there's some real challenges with the actual mechanism for publishing events. And that's actually where this whole mechanism of event sourcing comes in. So it's a long-winded explanation, but there's some quite complex technical kind of issues that you kind of have to dig into in order to see the motivation for event sourcing. So the whole big idea behind event sourcing is that it's a very event-centric way to designing your business logic. So the way it works is for each aggregate in your domain model, in other words, sort of the key business entities like an account or an order or the shopping cart, for example, and that's a term from domain-driven design, you actually identify the state-changing events. So for an account, it would be the account was opened, it was credited, it was debited. And you actually represent those explicitly in your domain model as event classes. So that's sort of a first thing you have to do. So you actually have to think about state-changing events and model them explicitly. But then where things get really different is that, rather than store the current state of a business entity in the database, so in this case it's the account where we just store, we have an account table which has a balance column, we just store the current balance. We don't actually do that. Instead, what we store in the database is the sequence for an entity, is the sequence of state-changing events. So we don't store the fact that the account has a current balance of 450. We store the fact that it was opened with a balance of 500 and credited with 250 and debited with 300. So we're storing the sequence of events. And then whenever we need to recreate the current state of a domain object, we actually just we query the database, load the events, and then we replay them back, and that will reconstitute the current state. And that actually in itself has a whole bunch of benefits that I'm going to describe in a minute. But what's really interesting and why this solves the problem of atomically updating state and publishing events in an event-driven application is, whereas before that was sort of a two-step thing, we updated the database and we published a message to an event broker, to a message broker. If all we're doing is persisting events and kind of implicitly publishing them, now we only ever have to do one thing, which is something that's straightforward to do in an atomic fashion. So in other words, whenever we persist an event in our event store, it gets published, and that's just a single atomic action. And so it's a very good way of implementing an event-driven architecture. And in the system, this is the way in which requests get handled, right? So imagine a request comes in to update, HTTP request comes in to update an entity. So the first thing you do is actually retrieve the events for that entity from the database. And then, in this case, we're going to create an account, right? So we actually just use the account's default constructor to create an account, or create a blank account object. And then we just we apply the events. So we process the open, we process the credits and the debits. And that reconstructs the current state of the account. And then we actually process the command which is coming from the HTTP request. And that actually gives us, instead of mutating the state of the account, it actually gives us events, a new event. So if it was a credit the account command, it gives us an account credited event. And then that event is just persisted in the event store. So we're just kind of constantly appending, whenever the state of an entity gets changed, we're appending new events onto its event stream in the event store. And there's actually an optimistic locking check that happens when we do the save to detect the scenario where the entity has changed since we loaded its events. And then, so that's how requests get handled, very event-centric. But then where it gets really interesting is that this event store basically, not only does it act as a store, it's like a database of events, but it also functions as a message broker as well. And subscribers can actually express interest, can subscribe to certain event types. And then when an event of that type gets published, gets persisted in the database, it actually gets published by the event store, gets consumed by the event subscriber, which can then update another aggregate, update another entity, which would then trigger the publishing of more events, or it could update some kind of sort of materialized view in some other database. So that's kind of how we keep databases in sync. So it's sort of a very event-centric way to implementing your business logic. And in terms of like, well, how do we, what is this event store? What are the implementations of it? Well, there's sort of a few out there, like quite a few folks actually just implement their own on top of a relational database. Greg Young, who's often primarily in .NET land, has an event store. And I'm working on one as a project as well. And it's really interesting stuff. And then the other thing you might be wondering is, well, gosh, I've got an entity that's very long-lived, and that could result in a very large number of events that need to get loaded in order to reconstruct its state. And that, for the most part, that's depending on your domain, that can be relatively infrequent. But if it does happen, one standard approach is to periodically take snapshots of a domain object, of an entity. So kind of like using the memento pattern, and you actually persist that in the database as well. So in addition to storing the events, you store snapshots. And then in order to load an entity, you just find the most recent snapshot and then find the events that have occurred since that snapshot was created, which is likely to be very few. So you actually can optimize the loading process. And then you reconstruct the state from the snapshot and the events. So that's a good optimization. So in terms of, well, what do these domain objects look like? So there's sort of two different flavors. If you go check out the GitHub repo, you'll see a couple of different flavors. So one of them is sort of a more traditional kind of OO with a functional sort of, slight functional flavor to it. And there's a couple of interfaces that your entities need to implement. Well, the primary one is command processing aggregate, which actually has a process command method that takes a command and gives you back a sequence of events. And then there's also and that actually extends the aggregate interface that has an apply event method. So we've got process command that takes a command, gives you events, and then you have apply event that takes an event and gives you back an updated entity. And here's an example of that. So here's an account class. So you can see there's process command that it's using Scala pattern matching, so which says if there's an open account command and for an initial balance is that, then return a sequence of just one event, the account opened event. Then likewise for credit, here there's actually a guard that's doing an overdraft check rather. So making sure that the amount is less than the current balance of the account. And then if you end up down here, then you're doing a debit for greater than the current balance of the account. And that actually results in an account debit failed due to insufficient funds event. So we're actually even though it's not actually changing the balance of the account, we're actually tracking the fact that we had an unsuccessful debit. And if anyone here works in a bank, I apologize, because I have zero knowledge of how banking works, but this is my best guess. Oh, yeah, there should be significant overdraft charges. Okay, so, and then the other part of this is apply event. And what that is basically, it's a sort of, it's doing pattern matching to say if the event we're trying to apply is the account opened event, then actually this is kind of a very cool feature of Scala, is that because the account is a case class, it has a copy method that's doing a shallow copy. And then we can just copy it saying the balance is this, right? Whereas if it's a debit, we can copy it saying the balance is the balance minus the debit amount, and likewise for a credit. So it's sort of leveraging both pattern matching and case classes to implement this. But at least, so it's kind of different, right? And like in real domain objects, there would actually be a significant amount of logic to do with command processing and account processing. And then it starts to look a bit more like regular objects. But because this is a, somewhat trivial example, it's sort of dominated, the code is dominated by a process command and apply event. And then the event store has an interface like this, where it's got a save method for saving a new domain object. And you pass in the events, and then an optional ID that can be assigned, otherwise it will generate one. Update appends events to an existing entity, and then there's a find method, a couple of find methods. And you can see that both of these return futures. So this is sort of a reactive async style of API. So that's sort of the kind of the more OO one, where you have to implement the command processing aggregate interface. And then there's a more functional one that actually separates out the state from the behavior and doesn't require any inheritance. So once again, you got an aggregate interface that's kind of looks similar. It's got an apply event, but the apply event method actually takes an aggregate and an event rather than being a method on the aggregate itself. And then there's a command trait that has a process command that takes an aggregate and a command and returns back events. So instead of you implementing these instead of your aggregate implementing these are actually Scala style type classes or implicit classes. And then the aggregate kind of consists of two things, right? Where you've got the actual aggregate, well, the money transfer aggregate is just a bunch of values, just pure state. And then the money transfer aggregate actually implements the process command and apply event methods. So it's kind of more functional separation of data from behavior, which functional people tend to prefer. And then the event store kind of looks fairly similar. The one difference is that the aggregate, which defines all of this behavior, actually gets passed in as an implicit parameter. So it's kind of like injecting a strategy. So it's telling the event store for an aggregate of this type how to actually reconstruct its state or how to save it, etc. So it's kind of an interesting style. Most of the code I've written was actually written in the first style, where I'm implementing specific interfaces, and this is a newer style, which is kind of nice in the sense that, there's no special, our entities don't implement any special interface, which is quite nice. So kind of why do this, right? Why use event sourcing? And there's really, a bunch of business benefits, right? So imagine you're working on an app and you have to implement audit logging, right? You have to track every change that every user ever makes in the system. The way you normally do that is to take your code base and sprinkle audit logging code throughout your code base, right? Which is, sort of the standard approach. Downside, of course, is if you ever forget to add the right audit logging call into your code, you've got a hole in your tracking. Now, the nice thing about event sourcing is because every change results in an event, you've got this 100% accurate audit logging mechanism. You can always look back at the stream of events to see who did what when to a given entity. It also enables temporal queries. In a database way where the standard approach is where you just store the current state, there's no way to actually go back in time and see what was the state of this entity 3 days ago. Where in this system, because we're storing the sequence of events, you can always go back in time and ask questions like that. So you could, if ever you need to look back and find out what the state of the universe was, you can do that in this system. And this architecture is always, it publishes events that can then get fed into some big data, machine learning, predictive analytics system to figure out how to personalize say the UI to the user, show them better cat pictures and the like. And it also preserves sort of the history of everything that's gone on in the system, and which means that you can actually implement a new feature today, but basically implement it as if it was, but basically do it in a fashion as if you'd implemented it at some point in the past, because you have all the events that corresponding to all the actions that a user has ever done, and you can feed them through this newly implemented component and construct state as if it had been functioning for, say, 6 months. So it kind of lets you sort of more easily implement features that you kind of hadn't anticipated. And then, of course, on top of that, there's a bunch of technical benefits, right? Like, it really does solve all these data consistency problems in a microservice NoSQL architecture, where we do really have all these databases that need to be, or views that need to be kind of kept consistent. And it also eliminates the OR mapping problem as well, right? That's sort of plaguing us forever, right? Like, I've got some complex domain object. How do I map that to the database? Well, in this system, what's getting persisted are the events, which generally are a lot simpler than the actual domain objects. So we've kind of, in best case, we've actually eliminated it, and the events just have a nice flat structure. In some domains, the events themselves could have some complex structures, but at least we've simplified the OR mapping problem, which is really important. Obviously, there's some drawbacks to building systems like this, right? Number one, it's kind of it's weird and unfamiliar at a certain level, right? It's not the standard way that we've been storing state or writing our domain logic. So it can take a little bit of getting used to. The events, which are immutable, right? We can't, unlike with a database where we can always apply schema updates to like refactor away any bad design decisions, the events tend to be immutable, right? Once it's happened, you can't go back and change it. And so there's a risk that they can be a historical record of like all of the bad mistakes that you've made. Though what's really nice is that in general, the events really correspond quite closely to things from the kind of the problem space. And so they tend to be kind of clear and well-defined, as opposed to being kind of artificial constructs from the solution space, which we're much more likely to screw up, right? Like, domain experts tend to have a much better simpler view of the world than, say, engineers who like to make things kind of complicated. Now, one challenge you do have is, it's a message-driven system, right? And there's always the possibility of duplicate events, which sometimes don't matter if the actual action of applying the event is idempotent. Whereas, let's imagine in some table you're maintaining the current balance, and so you want to sum up the sequence of credits and debits. That is not an idempotent operation, right? And if you see the credit event twice and don't detect it, the current balance is going to get out of sync. And so you have to do things like detect duplicates, which in general is pretty straightforward to do. You just keep track of the most recently seen event ID and discard anything that isn't later than it, right? So most cases it's pretty straightforward. It's also a little tricky that, well, we're changing things in one table, and then we might be kind of querying another table over here, which is derived from the events that haven't been processed yet, and so our application could, in theory, see inconsistent data. And so that can be a challenge. I mean, it's not, insurmountable. And then the other challenge you have is that the event store itself only supports primary key-based lookup. What are the events for this entity? It doesn't support queries. And that's where command query segregation comes in, which I'm going to talk about in a little while. So, okay, so we've kind of decided, we've gone down the event sourcing route. So sort of what is our, and we're using microservices, so what does our system look like? So, whenever you're designing a system with microservices, first thing you have to kind of do is, well, what microservices am I going to have? And sort of a first high-level pass at that really is, well, what are the, in domain-driven design terms, what bounded contexts am I going to have? Which really is a way of saying, well, in this problem space, what are the subdomains, what are the sort of functional areas, what are the subdomains? And usually each one of those maps to a given microservice. And then within a given bounded context or microservice, you kind of then have to look at your domain model and break it up into aggregates, kind of self-contained little clusters of objects. So they identify like the order aggregate, the account aggregate, and so on. And then the microservice, each microservice really is just a set of aggregates. And remember, one of the interesting design constraints with an aggregate is a transaction only updates one aggregate at a time, which is kind of different from the standard way of doing things. But then, so we've got some aggregates. Then we also have to have some adapters that are handling requests that are coming in from the outside world, HTTP requests. So that sort of translates into like Spring MVC, for example. Or maybe they could be requests coming in over some other message broker, right? So there's some kind of integration adapter. And those are taking these requests to update an aggregate and turning them into commands that are being processed by the aggregate. And then events are getting saved into the event store. And then at the same time, there's another adapter that's consuming events, that's subscribing to events being published by the event store and translating them into commands as well. So commands are sort of coming in from the outside world, and they're also coming in from event or being generated from events that are being published by the event store. So if we were to look at some example code, so here's an HTTP adapter, which is basically a Scala Spring MVC method or controller that's just handling requests, HTTP post request to the transfers URL, and it's creating a money transfer object. And the only reason it looks a little more complicated is that this is all written in a reactive style. So money transfer or transfer money is returning a future that's then getting mapped back into a Spring MVC deferred result, which is itself yet another kind of future. And that's how you're using how you use an asynchronous or a servlet asynchronous API. So then the money transfer service looks like this. So there's a transfer money method that's saying, I need to transfer money from this account to that account. And then this method is written in terms of a kind of mini domain-specific language that's saying, go create a new entity of type money transfer and have it process the create money transfer command, right? So we're creating a command and we're feeding it into a brand new money transfer aggregate. And what that's doing, what sort of that's encapsulating is the boilerplate of creating a new aggregate, processing that command to yield events, applying those events to the aggregate to update it, and then persisting the events in the event store, which is then causing them to get published. And then here's what one of the event handler adapters look like. So this is consuming events that are coming from the event store. So in this case, it's the account debited event handler. And it's actually updating the money transfer entity, an existing one, whose ID is from the transaction ID attribute of the event, and it would telling it to process the record debit command. And what that's doing under the covers is loading the specified money transfer aggregate, processing that command, which generates events, applying those events to update the aggregate, and then persisting the newly generated events into the event store. So we kind of seen how we handle HTTP requests through the controller and the service, and then this is how how events that are being published by the event store trigger updates as well. And so that's kind of the style of the business logic, and for me it sort of worked out quite well. And you know, obviously it's like leveraging Scala really heavily. If you actually go look in my GitHub repo, there's also a Java Spring version of that, which just like way more code, right? Even simple things like defining the event classes in Scala, it's just sort of a one-line class definition, which in Java translates into, so you got 5 event classes, that's 5 lines of Scala code. In Java, that translates into 5 separate Java files, and each one has like 20 lines of getters and setters and stuff. It's it was hard typing all that in. Anyway, so but the examples are there if you want to see the Java flavored version of it. So one of the limitations of event sourcing I talked about is just the fact that the event store itself only supports primary key-based lookup, right? What are the events for a given entity? But if you think about, you know, how we build, you know, the requirements of most applications, we need to do queries that are more elaborate than that, right? So maybe we need to display the current balance of an account and the most recent end transactions for that account, right? So that's basically doing a join between, kind of conceptually doing a join between accounts and transactions. And obviously that doesn't fit into the event sourcing model, right? Where we can only retrieve events by primary key. And so the idea here is to use the CQRS pattern, Command Query Responsibility Segregation pattern. And what that does is actually split the system into 2 pieces, right? The command bit, command side, which is actually processing commands, processing updates. And that's what I've been talking about up until this point. And then there's the query side, which is sort of another part of the system that all it does is handle queries. Hence the term we're segregating or separating responsibilities, where one module handles queries, the other module handles commands, which is very different than the traditional way we construct systems, right? Which actually, you know, a given domain object and a given database schema is designed to handle both updates and queries. But in this system, so when an aggregate is updated, right, events get published or get saved and then published by the events store, and then they get consumed by the query side, which uses those events to update a denormalized or materialized view of the data, which is query friendly. And so to dig into the query side a little bit more, so the query side uses one or more different kinds of databases, right? And the databases that you use depend on the types of queries that you need to support. So it could be a relational database if the queries are supported by a relational database. They could be a text engine like Cloud Search or Elasticsearch if you need to do text style queries. Or it could be a graph database, if like Neo4j, if you're querying like social data and so on. And so also not only there could actually be multiple views depending on, you know, if you need to support multiple kinds of queries. Then there's a microservice that's consuming events and actually updating the view. right? So it's just responsible for just processing all of the events that are being generated when changes are happening, and then effectively building up these materialized, denormalized views in the view store. And then there's another microservice that's handling the HTTP GET requests and running queries against the view store. So we really have separated things out. And so like one of the examples I have, right, is I'm using MongoDB to store for each account its current balance and the recent transfers that have transferred money in and out of that account, and also the sequence of debits and credits that have operated, that have modified that account. And all of that ends up being, for each account, there's just one MongoDB document that's storing all of that data. And then, you know, a simple kind of, there's a set of event handlers that are subscribing to all of the relevant kinds of events and actually finding the appropriate document and either creating it or finding it and updating it. And then in order to, so there's just, and then by looking up that document by primary key, you get all of the data that's needed to view the current balance and all the recent transactions. And that's sort of just, and that's sort of super efficient because we've basically pre-joined all of the data versus having to do a multi-way, probably outer join against some SQL tables. And so Mongo's doing it in a much more efficient fashion. And then, you know, in the system I've been building, I've actually been using Cloud Search for doing, which is AWS's hosted text search service. So that's sort of been working well. And then actually for the other views in the app, I've been using DynamoDB, which is Amazon's NoSQL as a service database. Basically, it just lets you do primary key lookup, and your entities look like little hash maps. So CQS, you know, it's a real interesting approach, right? It actually is necessary in an event source system to support queries. It also has the benefit that you really are separating concerns, right? You've got one model that's doing command processing, and then you've got another model that's handling queries, and by separating them, you tend to, each one is much more, you know, is obviously focused on one thing and tends to be a lot simpler than if you had kind of mixed it all up together. And it also supports multiple denormalized views. As I said, you could actually have a text search engine, a graph database, and MongoDB all being updated from the one event stream, and each one's, you know, each different type of database supports different queries, you know, in the most efficient fashion possible. And so it tends to improve scalability and performance of your system. But on the other hand, you know, there's obviously complexity, right? Like there's all these different parts, moving parts in your system now. There's the risk that you might actually have to duplicate code between the command view and the query view. And there's also the whole replication lag thing, right? Where you update something on the command side, there's a finite delay before the corresponding view gets updated, which can, you know, sometimes that matters. Often it does not. But you can always play games like in the UI. You can always optimize, you know, if say the UI is a, you know, it's a JavaScript client, right? You can always optimize, when the user hits the save button, the UI can always optimistically update it, send off the request to the server to do the update, but then optimistically update its model and what the user sees with the assumption that that update's going to be applied, and then by the time the user ever requests the data from the server, the update really has been applied to the view. And so you can kind of hide any replication lag just by having a smarter client. Okay, so that's CQRS. And now I just sort of want to change gears and talk about some sort of nuts and bolts of deploying this application. So yeah, architecturally it looks like this, where there's a bunch of services that are implementing business logic, and they're all implementing it using event sourcing and the like. They're plugged into the event store. There's a couple of like one infrastructure service that's actually just subscribing to all events for all entities and actually just archiving the events into S3. There's also an indexer that's, whenever entities change, re-indexing them in Cloud Search so I can do text queries. And then in front of the services, there's an API gateway that's written in Node.js, and that's basically incoming. It provides basically a single entry point. And then when a HTTP request comes in, it actually routes it to the appropriate backend service. And then in a few cases, it actually calls multiple backend services and like aggregates the data together and returns it to the browser. So that's sort of the highlight. Oh, and all of the interesting stuff's really implemented using Scala. And then the services themselves are all implemented using Spring Boot, which I find absolutely fascinating technology. I've been a fan of Spring for, I guess, 11 years now, real long time. And Springs just continue to be awesome. But then Spring Boot came along, was it a year or two ago, and it was like, wow, this is really changing how you build Spring applications. And yeah, if you're not familiar with it, the whole goal with Spring Boot is that it makes it really easy to create standalone production-ready Spring applications. And one of the things it does, it actually uses convention over configuration in a really smart way to eliminate a lot of the configuration metadata, in other words, sort of like XML and Java config, that you would otherwise have to write, which is just huge. Really, you end up with these apps that do a lot, but you've actually had to write very little configuration metadata. And it also does things like externalize configuration for, say, database host and port and credentials and message broker host port credentials and so on. Can read that from environment variables. And then it also has plugins from Maven and Gradle that make it very straightforward to create standalone executable jars that actually have Tomcat and/or Jetty embedded inside the jar, so you never have to actually install your own Tomcat in order to run the app. You just go java-jar, and it's sort of, it's just huge. And maybe if you're building a monolithic application, you don't need much of this, right? Because, well, you just have one app, and you probably set up the configuration and the setup for that 5 years ago. Whereas in a microservice style architecture, you're constantly building new services, and so you kind of need all of this sort of kind of foundation that Spring Boot provides just over and over again. So it's really exciting. So as I said, big feature with Spring Boot is that it sort of kind of minimizes the amount of configuration metadata that you supply. If you've used Spring, then you sort of recognize this, right? Where you have your application components, then you have metadata that's either, well, in the beginning it was XML, and then it sort of evolved into annotations, and now you can use them. In addition to those, you can also use type-safe Java config as well. And that metadata says, well, here are my components, my beans, and how they all fit together, and what needs to be transactional, and all of that. And that all kind of gets sucked into the Spring container, and you have this fully configured app. So when you start using Spring Boot, basically Spring Boot kind of supplies all of this default configuration metadata for you. And it basically looks at the class path and says, oh, you've got a JDBC, you've included a JDBC driver, therefore you need a data source and a transaction manager. It's kind of got all these rules for inferring what beans that you should have based on what jars you have on your class path. So the net result is you end up having to write very little configuration data, metadata. So like one of the demo apps I have, that's kind of it, right? Everything else, it's actually talking to RabbitMQ, and I think it might be using MongoDB as well. But that's most of the configuration for an app, which compared to what you had to write before is relatively tiny. And the only reason I had to write this is just because I needed to tailor how the RabbitMQ template was serializing Scala objects to from JSON. So it's very exciting. And so the actual mechanism that it's sort of relying on is kind of just base features in the Spring framework itself, right? So things like enable auto configuration just sucks in, that's kind of the Spring Boot annotation, sucks in a whole bunch of default configuration, which then uses a conditional bean mechanism to figure out which beans that you should add should be defined in your system. And there's kind of like two types of conditional configuration. So one type is, well, if this class is on the class path, right? In other words, if there's a Mongo driver or a MySQL driver, then that says, well, you obviously must need either the Mongo related Spring Beans or the JDBC related Spring Beans, right? So it just kind of sets those up. But then the other kind of level of sort of conditionality is, well, if you haven't defined a bean of this type, then I'm going to define it for you. So that's the way that you can define some of these beans yourself and override the defaults, which actually you rarely need to do, but the net result is all this default config just kind of gets defined for you. And then the way that you kind of have the main program is sort of no web apps anymore, right? It's just an executable jar, and the main program looks like this, and that's basically Spring application.run passing in the main config class and then the command line arguments, and you're good to go. And then the build process, just there's Maven or Gradle plugins that create an executable jar. Oh, and the other part of it is there are these starters, right? Always an ongoing problem with Spring was there's all these different jar files that you have to import, and you have to make sure that you get a consistent sort of configuration. Well, with Spring Boot, you just import the relevant starters. You depend on the relevant starter artifacts, and they actually pull in consistent sets of dependencies. So the Spring Boot starter web pulls in all of the jar files that you need for a Spring MVC application, right? Likewise, Spring Data Mongo pulls in all the Spring jar files and dependent libraries that you need for a MongoDB application. So even your Gradle or Maven POMs get a lot simpler. And then when you run it, java-jar, and then you can specify command line args, or it will pick them up from the environment. And then what's really cool is you get built-in health checks as well. So you get a health URL that you can just ping, and it gives you information about the state of the application, which is handy. Like I actually have that hooked up to New Relic in my app, and I get alerts if things don't work. So all this stuff that you would otherwise have to build just kind of comes out of the box, and so it's really cool. So the other cool thing that's sort of super new these days is kind of the whole Docker phenomenon. And so each one of my microservices, I have this like multi-step pipeline in Jenkins that first off builds and tests the microservice. So out of that comes a tested executable jar. Step 2 actually packages that jar as a Docker image and actually tests that the Docker image starts up okay. And then the third step is publishing it to to a registry. And there's like one of these pipelines per microservice. So there's so in terms of Docker stuff, so I run the Docker build command, and that actually takes my jar file, packages it up as a Docker container, and that actually takes about 5 seconds, which is, compared with building an AMI, for example, right, which takes minutes, it's orders of magnitude faster. I mean, it's funny, when I heard about Docker, I thought, oh, it's just like lightweight virtual machines, no big deal, right? And then I actually tried it, and it's like, when things are orders of magnitude faster, they're like something different entirely. And, oh yeah, then the other thing I do is I do a smoke test on the Docker image. So the test actually uses the Docker daemon REST API to actually create a container from the image, start up the container, and then actually pings the health check URL just to make sure that it's like working and nothing sort of really stupid has been broken. And then it's published using another couple of Docker commands. And that actually and the actual registry lives in S3, so that, for some reason, that actually takes 25 seconds to do the upload, which in a way is sort of kind of takes ridiculously long, actually, but it's doing a lot of, I don't know, for some reason the upload process there's a lot of kind of analysis happening, I think. So my actual runtime environment is a large EC2 instance with a whole bunch of Docker containers running on it. But then what's really interesting is the actual build environment itself is actually running in Docker as well. So both Jenkins and Artifactory are both deployed as Docker containers on my build machine, another EC2 instance. And the only thing of note here is that because I need to preserve Jenkins home and Gradle home and also Artifactory home across container restarts, those directories actually live outside of the image, outside of the Docker image, and then are mapped into the Docker image when it's launched. And they actually reside on an EBS volume just in case the whole build machine goes away, right? So, but anyway, it was kind of cool actually having, a Jenkins running in a Docker image, building other Docker images. Kind of like that movie Inception, I think. Actually, I even had, like, at one point, Docker running, the Docker that Jenkins was using to actually test the images was actually running inside the Docker image. And that got weird, so I took it out. And now Jenkins talks to the Docker that's running it to launch the test image. And then in terms of the production environment, as I mentioned, that's just a large EC2 image instance that's got Docker running on it. And then the way I actually update it right now is, I'm using the most primitive thing possible. I actually have a Python script that's actually looking at what Docker containers are running, compares their versions with the Docker containers that Jenkins has built using the Jenkins RPC library, and just does a comparison, and if anything needs to be updated, it actually runs Docker commands to pull down the new image, stop the old container, start the new one. And then at some point, I need to switch to something more sophisticated, like a proper multi-machine Docker clustering solution. And for that, I'm hoping that AWS EC2 Container Service, which is kind of in a preview state right now, will be mature enough to use. Otherwise, I have to figure out how to get Kubernetes up and running on EC2. So anyway, it's kind of the whole experiment was sort of fun, right? Just radically sort of different architecture, right? Event sourcing with microservices and NoSQL databases, with CQRS, and then using Spring Boot, which, as I said, super excited about, and actually using Docker. as well, which is super exciting technology that's kind of like transforming the whole deployment thing. Anyway, so that's my talk. I thank you for listening, and I hope that you found it useful, and I'll happily take questions. Yeah.
Question on the event store. So you built your own implementation, it looks like?
Yes.
Could something like a durable queue substitute for an event store?
Yeah, so the question is, could a durable queue substitute? Well, it turns out that an event store is kind of like half database, right? In the sense that you need to be able to persist events and retrieve events per entity. And you can actually, and also it's a message broker as well, right? And so it's sort of, I remember someone asked me, well, couldn't I just use Kafka, right? But the problem you have is that, in theory, you can model each entity as a Kafka, as a queue, right? Some kind of durable queue. But most message brokers couldn't scale to support a gazillion entities, right? They're not designed to scale in that dimension. So not really. And so actually the event store ends up underneath, sitting on top of a database and a message broker, and it's effectively coordinating updates across both of them. Yeah?
How do you protect against the loss of events or recovering events that maybe might have been lost or by other conditions that exist that are lost? So like say your database is storing event, there's an issue.
Oh, so how do you protect?
That you're not missing any events.
Well, so number one, I'm using a very supposedly reliable message broker, right? Which itself is highly available. So that should give you a fair level of comfort. And then other than that, it sort of depends what you're doing, because certainly on the view side, right, like if you are, number one, if you're archiving all of the events, right, like I'm doing into S3, you could actually, for a view, you could actually reconstruct that view from scratch by processing all of the events that have ever occurred. Which is somewhat analogous to the Lambda architecture, right, in big data, except that the assumption here is that the event processing has a high degree of reliability, and you're not you don't need to recreate from scratch. Yeah?
So I was hearing about this. It started sounding very familiar, and then when I'm looking at it, it seems like almost like RDBMS design, like database design. It has journaling, snapshots, playback. Same with like source control versioning, where there is essentially you're just storing the events that are happening. I'm curious about like what's your opinion of like are we just like taking that and essentially expanding it to be more general purpose than what it is right now?
Yeah, so that's a great observation. Yes, in a way, what event sourcing is basically sort of moving the transaction log up to the application level in a way. Then the notion of storing deltas. That's like CVS, right? Or the original one, SCCS, if you can remember back that long. So yeah, it's kind of, it's the joke, right? There's nothing new in computing. It's just there's a few ideas that get repackaged and reapplied in different areas. And in some ways, it's like this.
Got it. No, it's cool because that means that there's probably a body of science that we can go and read about and see if there's anything else we could apply.
Yeah. So, yeah.
Are there particular domains that you think this kind of event sourcing approach is well suited for versus, or actually even better, some that it's not well suited for?
Yeah, that's so it's sort of, yeah, what domains is it suited for, not suited for? I think I think it probably works best in systems where there's significant amount of business logic, right? Like if you think about, say, the domain model pattern versus like transaction scripts, right? Domain models best if you've got complex it's a complex domain, real business logic. Whereas if you're just sort of doing CRUD, then scripts and stuff like that. And so if you look at event sourcing as a way of implementing a domain model, it's like, well, when you would use a domain model, right, is when you could use event sourcing plus then there's the issue of the context where you're using it, right, in the sense that do I have multiple databases that need to be replicated, right? Do I need to use an event-driven architecture? Do I need accurate audit logging? Is OR mapping burdensome? Do I need temporal queries, right? So those are sort of the questions that are worth asking as to whether you have the problems, you need to solve the problems that event sourcing and CQRS solves.
So kind of a related question would then be, is there a problem you see in trying to hybridize this with another solution? Because this kind of seems like it operates as sort of a closed system with everybody playing by the same rules versus if you were trying to bolt it onto an existing...
Oh, thank you. Yeah. Well, one interesting thing you can do is, like if you need to integrate with a legacy system, right? That legacy system's generating events, those events can actually be fed into the event store system as kind of like you end up mirroring entities that are in your legacy system. So there are integration strategies. Yeah.
How do you handle it when you don't yet know the identity? So for instance, let's look at an account generation, so I'm generating an account. Well, generating the account, so from the ones you generate, they're going to have the identity for the account. But when how do you bootstrap that? How do you give it the initial ID and know that you're not also giving that ID to some other account?
Oh, okay, yeah. So the question is like, how do things end up with unique IDs? So when you save an entity for the first time, you can optionally specify an ID, right? So that's sort of like some natural key from the domain. But if you don't specify an ID, then the event store generates one for you that is guaranteed to be unique. Well, thank you, and I'll just be up here if anyone else has questions.